Tomorrow morning, at almost exactly 6:35 UTC, a 4-ton, 39-foot-long piece of dead space hardware is going to slam into the surface of the moon at roughly 5,400 miles per hour, gouging out a brand new crater in a spot near a 100-year-old impact scar called Einstein Crater, close to the moon's western edge as seen from Earth. If you've seen a headline promising that the moon is about to do something it hasn't done in a century, that specific number isn't quite right, and we'll get to why in a minute. But strip away the exaggeration, and what's actually scheduled to happen tomorrow is genuinely one of the more remarkable, precisely predicted events in the history of spaceflight. An event that astronomers have been quietly tracking, refining, and preparing for since last September. And one that's about to give scientists a front row seat to something they've almost never had the chance to properly observe before. A human-made object hitting another world in real time, with cameras and telescopes actually pointed at the right spot when it happens. Let's start with what this thing actually is, because it isn't a meteor, it isn't an asteroid, and it isn't some ominous, unexplained phenomenon. It's leftover space junk, and specifically, it's the spent upper stage of a SpaceX Falcon 9 rocket. Back in January of 2025, that Falcon 9 launched 2 separate missions toward the moon in a single flight. NASA funded lunar lander called Blue Ghost, which went on to successfully spend 14 days operating on the lunar surface, and a private Japanese lander called Hakuto-R, which was intended to touch down on the moon, but ultimately failed to land successfully. Once the rocket had finished its job boosting both of those spacecraft on their way, the upper stage itself, the second, smaller section of the Falcon 9 that doesn't return to Earth and get reused the way the rocket's first stage famously does, was left behind in space with nothing left to do and nowhere in particular to go. Most Falcon 9 upper stages either stay in orbits close to Earth and eventually burn up re-entering our atmosphere, or drift off into orbits around the sun entirely. This particular one did neither. It ended up settling into an unusual lingering orbit that kept bringing it back around to roughly the same distance as the moon itself, over and over for more than a year, essentially becoming a slow, tumbling piece of cosmic debris caught in a long, repeating dance between Earth and its only natural satellite. That's where an astronomer named Bill Gray enters the story, and honestly, his role in all of this is one of the most interesting parts. Gray has spent roughly 3 decades working as a contract astronomer for the asteroid hunting community, building software tools that help professional sky surveys tell the difference between genuine, potentially dangerous near-Earth asteroids and ordinary human-made junk drifting through the same patches of sky. That distinction matters more than you might think, because from a telescope's point of view, a tumbling rocket body and a small asteroid can look almost identical, just a faint, slowly moving point of light with no obvious way to tell what it's actually made of. Gray has been watching for exactly this kind of coincidence, an old piece of space hardware wandering close enough to the moon to actually strike it. For about 20 years now, and by his own account, he wasn't especially surprised when he finally found one. As he put it in comments to the science outlet Earth Sky, the real surprise, in his view, isn't that this is happening now. It's that only one other piece of tracked space junk has ever actually been confirmed to hit the moon before this. He first suspected this particular Falcon 9 upper stage was on a collision course back in September of 2025, and spent the following months quietly refining that prediction, tracking the object's faint, tumbling brightness through telescope after telescope, gradually narrowing down exactly when and where the impact would occur, without any single dramatic moment of certainty, just a slow, steady accumulation of increasingly confident data. And that precision is genuinely remarkable when you consider what Gray was actually trying to measure, predicting exactly where and when a spinning 4-ton hunk of metal drifting through space will eventually strike another world, months in advance, down to fractions of a second, requires accounting for forces most people never think about at all. The moon's gravity plays the obvious role, but so does the extremely faint, almost imperceptible push of sunlight itself, a phenomenon astronomers call solar radiation pressure. As the tumbling rocket stage catches sunlight at different angles while it spins, it can actually reflect that light slightly, sideways, nudging its trajectory by tiny amounts that are notoriously difficult to model precisely. Gray has spent months accounting for exactly that kind of subtle, wobbling uncertainty, refining the predicted impact site and timing right up until the final days before tomorrow's collision. It helps to understand a little more about how Gray actually does this kind of work, because it's a strange, oddly specific corner of astronomy that most people have never heard of. He describes himself as an astronomer working under contract for both the asteroid hunting community and, somewhat by necessity, the small handful of researchers who track artificial objects drifting far from Earth. He started out roughly 3 decades ago building software specifically meant to calculate orbits for natural objects like asteroids, comets, and the moons of other planets. A few years into that work, the major asteroid survey telescopes began noticing that their images occasionally contained something that clearly wasn't a natural object at all, a piece of human-made hardware drifting through the same patch of sky, and they started asking Gray whether he could help them calculate orbits for those artificial objects too, simply so they could rule them out and get back to searching for genuine asteroids. That side project has stuck with him ever since, and today he maintains what amounts to an informal, mostly one-person effort to track a small number of high-altitude artificial objects, roughly a dozen or so at any given time, that move slowly enough through the sky to occasionally be mistaken for natural asteroids by automated survey software. Countries and space agencies devote enormous, well-funded effort to tracking debris in low orbit close to Earth, precisely because there's so much of it there and so much risk of it colliding with active satellites or the International Space Station. But once you get out to the distance of the moon, that kind of careful, coordinated tracking essentially falls away, leaving objects like this Falcon 9 upper stage to be found almost by accident, noticed only because the same telescopes hunting for dangerous natural asteroids happen to sweep past them too. So, where exactly is this thing going to hit, and why does the location actually matter scientifically? The rocket body is expected to strike near a lunar crater called Einstein, close to the moon's western limb, meaning close to the edge of the moon as we see it from Earth, in a region where the lunar day and night meet along what's called the terminator line. That specific lighting condition wasn't a coincidence in how astronomers chose to study this event. It's actually one of the reasons scientists are so interested in watching this particular impact closely. NEO, or that day-night boundary, any dust and debris kicked up by the impact should catch direct sunlight against an otherwise dark lunar sky, potentially making the resulting plume considerably easier to photograph and measure than it would be if the impact happened out in the middle of the fully sunlit lunar day. Here's where the story gets genuinely scientifically interesting, beyond simply being a neat, precisely predicted event to watch. A research team at the University of Texas at Austin, led by a researcher named William Joe, submitted a study specifically modeling what this impact should actually look like when it happens, published just about a week before the event itself. Their calculations predict that the central spike of debris thrown upward by the impact, what scientists call the ejecta plume, could reach somewhere between roughly 45 and 60 miles above the lunar surface, with a broader curtain of debris spreading outward for something like 10 to 12 miles vertically, and material scattering laterally across more than 100 miles near the impact site. According to Joe's modeling, that plume should be dramatically brighter by orders of magnitude than the naturally dark lunar sky surrounding it, at least for the first few minutes, immediately following the impact, which means that with the right equipment pointed at exactly the right spot, at exactly the right moment, this plume should genuinely be visible from Earth. And this is precisely why scientists are paying such close attention to an event that is, on its surface, just a piece of space junk crashing into an airless rock. As Joe explained it, a spent rocket stage is a hollow, largely empty human-made object, and there simply aren't very many existing models describing how objects like that behave when they strike a surface, compared to the far more extensively studied behavior of solid, naturally occurring impactors like asteroids or comets. Early evidence suggests hollow human-made bodies tend to produce meaningfully different debris plumes than solid natural objects do. And watching this particular impact unfold in real time, with instruments specifically positioned and calibrated in advance, gives researchers a genuinely rare opportunity to test and calibrate their models against an actual verified precisely timed event, rather than trying to reconstruct one after the fact, from a leftover crater alone. That calibration isn't just academic curiosity either. It directly matters for every future spacecraft, lander, and piece of hardware humanity sends toward the moon going forward, because understanding exactly how debris behaves when something strikes the lunar surface has real, practical implications for planning safe distances, predicting hazards, and protecting future missions and astronauts working anywhere near an active or planned landing site. Now, will people actually be able to watch this happen with their own eyes tomorrow morning? Almost certainly not, at least not without serious equipment. The initial flash created by the impact itself is expected to last less than a full second, far too brief and far too faint for the naked eye or even ordinary binoculars to catch. Seeing anything meaningful is going to require a telescope with a reasonably large aperture, ideally paired with high-speed video recording equipment capable of capturing extremely brief, faint flashes of light against the darkness of space. Timing and location matter enormously too. The predicted impact window favors observers across the eastern half of the United States and Canada, along with much of South America, where the moon will have already risen above the horizon by the time of impact, sitting near its last quarter phase with the planet Saturn visible nearby in the same patch of sky. For most casual skywatchers, even in those regions, this is going to be an event experienced through published telescope footage and scientific papers in the following days, rather than something visible by simply stepping outside and looking up. Interestingly, amateur, astronomers have already spent recent days actively tracking the tumbling rocket body as it approaches its final trajectory, and their observations have actually helped refine the impact prediction even further in the last stretch before tomorrow's event, adjusting the expected impact point slightly farther toward the moon's edge than earlier estimates suggested, which unfortunately makes the plume marginally harder to observe from Earth than originally hoped, though still very much worth professional observatories attempting to catch. It's worth appreciating, too, what kind of place on the moon this rocket stage is actually about to strike, because the target itself has its own quiet history. Einstein Crater sits out near the moon's western limb, a large, ancient, heavily eroded impact basin named after the physicist, formed by a natural collision so long ago that its own rim has been softened and reshaped by billions of years of smaller impacts landing on top of it since. It's not a particularly famous crater compared to some of the moon's more recognizable features, and it isn't the kind of place casual observers typically point a telescope at, but its position right near the edge of the visible lunar disk, close to where the moon's day side gives way to its night side at any given moment, happens to make it a genuinely useful location for exactly this kind of observation. Not because anyone chose the target on purpose, but simply because that's where months of careful orbital calculation happened to place it. There's something almost fitting about a fresh 21st century piece of space debris coming to rest near a crater named after one of the physicists whose work on gravity and motion ultimately made it possible to calculate, with this kind of precision, exactly when and where that debris would land. Now let's actually address that headline claim directly, because it's worth being honest about where it comes from and why it doesn't hold up under close inspection. This is not the first time a piece of space debris has struck the moon, and it isn't remotely close to a 100-year gap since the last comparable event. Back on March 4th of 2022, Bill Gray, the very same astronomer tracking tomorrow's impact, predicted an earlier rocket body collision with the lunar surface, an event that did indeed occur almost exactly as predicted, striking near a different lunar crater called Hertzsprung and leaving behind a distinctive double crater roughly 100 feet across, later photographed directly by NASA's Lunar Reconnaissance Orbiter as it passed overhead. That 2022 event actually generated a fair amount of public attention and confusion at the time, too, partly because there was initial uncertainty about which country's rocket had actually caused it. So tomorrow's impact is genuinely only the second time in recorded history that astronomers have successfully predicted, tracked, and confirmed a piece of space junk deliberately colliding with the moon, not the first in a century. What does make tomorrow's event genuinely unprecedented, though, and this is worth appreciating on its own terms, without needing to inflate it into something it isn't, is that it's expected to be the very first predicted lunar impact in history to strike the side of the moon that's actually visible from Earth. The 2022 impact happened on the moon's far side, permanently hidden from any direct observation from our planet, meaning scientists only ever got to examine its aftermath secondhand through orbital photography taken well after the fact. Tomorrow's impact, striking near the moon's visible western edge, gives astronomers something genuinely new, a real chance to actually watch the event itself unfold in something close to real time, rather than simply documenting the crater it leaves behind afterward. It's also worth putting this event in a slightly broader context, because it says something interesting about just how much orbital debris humanity has already scattered around near Earth space, largely without most people ever noticing. There have now been hundreds of individual Falcon 9 launches since SpaceX, Falcon 9, began flying the rocket regularly, and while the reusable first-stage booster typically returns to Earth and lands for reuse, becoming something of a signature spectacle in its own right, the upper stage almost never does. Most of those upper stages either burn up, harmlessly re-entering Earth's atmosphere within months or years, or drift off into long-term orbits around the Sun, where they're essentially forgotten. This particular one is unusual specifically because it settled into a long, lingering orbit that kept looping back toward the distance of the moon repeatedly for well over a year, rather than quickly re-entering or drifting away entirely. Objects in that kind of high lunar distance orbit are, according to Gray, generally poorly tracked compared to the much more heavily monitored debris field closer to Earth, where multiple countries actively watch for potential collisions with active satellites and the International Space Station. Farther out, toward the moon's distance, that kind of careful tracking essentially doesn't exist in any organized, comprehensive way. Aside from the incidental efforts of asteroid hunting surveys, which stumble across objects like this rocket stage purely as an unwanted byproduct of scanning the sky for actual, potentially hazardous natural asteroids. As Gray has put it himself, those surveys would honestly prefer not to have to deal with space junk cluttering their images at all, since every minute spent puzzling over a piece of human-made debris is a minute not spent searching for a genuinely dangerous natural object. But because both rocks and drifting junk appear in their telescope images as nearly identical, slowly moving points of light, the The surveys end up finding this kind of debris, whether they're looking for it or not. There's a certain fitting irony buried in that fact, actually. The same network of telescopes built specifically to protect Earth from the genuine, if statistically rare, threat of a dangerous incoming asteroid is also, almost as an accidental side effect, the exact system responsible for spotting humanity's own forgotten hardware quietly drifting back to collide with our nearest neighbor in space. And once an object like this is caught by those surveys, distinguishing it definitively from an actual asteroid, and then calculating precisely where and when it's going to end its journey, falls to specialists like Gray, working carefully behind the scenes for months, refining a prediction most people will never hear about until a headline eventually announces, sometimes with more drama than the science strictly calls for, that something is about to happen to the moon. So what should you actually expect to see, or more accurately, expect to read about, once tomorrow morning's impact has come and gone? If everything goes according to the current predictions, at 6:35 UTC, a hollow 4-ton rocket stage will strike the lunar Giza, surface at roughly 1.5 miles per second, carrying kinetic energy equivalent to somewhere in the neighborhood of a few tons of TNT. Because the moon has no meaningful atmosphere at all, there will be absolutely nothing to slow that object down or burn it up before impact, unlike what happens when debris re-enters Earth's atmosphere. The impact should gouge out a fresh crater, somewhere between roughly 20 and 30 meters wide, considerably smaller than the crater a solid asteroid of comparable size would create, precisely because the rocket stage itself is mostly hollow, empty structure rather than solid mass. In the minutes immediately following, professional telescopes and specialized imaging equipment positioned across the eastern Americas will be watching closely for exactly the kind of debris Plume William Joe's team modeled in advance, hoping to catch real, measurable data on how it rises, spreads, and eventually settles back down onto the lunar surface. And sometime in the days or weeks that follow, NASA's Lunar Reconnaissance Orbiter, the same spacecraft that photographed the aftermath of the 2022 impact, is expected to pass over the new impact site and, if the timing and geometry line up correctly, capture direct images of the fresh crater itself, giving scientists a final, concrete confirmation of exactly what tomorrow's carefully predicted collision actually left behind. It's also worth stepping back and asking why any of this actually matters beyond being a neat, precisely timed spectacle for telescope owners to chase. Humanity's relationship with the moon has changed dramatically over just the past few years. NASA and multiple international and private partners are actively working toward returning astronauts to the lunar surface for the first time in over half a century, alongside a growing wave of robotic landers, like the Very Blue Ghost and Hakuto R missions. This same rocket helped launch, aimed at scouting future landing sites, testing new technology, and eventually supporting a sustained human presence there. Every one of those missions eventually generates its own leftover hardware, its own spent rocket stages, discarded landing gear, and abandoned equipment, much of which will, sooner or later, end up doing exactly what this Falcon 9 upper stage is about to do tomorrow morning, falling uncontrolled back down onto the lunar surface somewhere. Understanding precisely how that kind of hollow human-made debris behaves on impact, how far its ejecta plume travels, how large a crater it actually carves out, and how predictable or unpredictable its final resting place turns out to be, isn't just an interesting one-off curiosity. It's directly relevant safety, and planning information for an era in which the moon is rapidly becoming a far busier, far more heavily trafficked place than it's been at any point since the last Apollo mission left in 1972. Tomorrow's impact offers scientists a rare, almost laboratory clean opportunity to gather exactly that kind of real, verified data, under conditions specific enough that researchers can actually check their predictive models directly against reality within days, rather than waiting years for the right kind of accidental impact to eventually happen on its own. None of that requires exaggerating the story to make it worth paying attention to. A team of astronomers accurately predicted, nearly a year in advance, the precise second and location at which a specific piece of human-made debris would strike another world, using nothing more than careful, patient tracking of a faint, tumbling point of light through ordinary telescopes. Researchers built detailed physical models predicting exactly how the resulting debris plume should behave. Based on physics, we've genuinely never had a clean opportunity to test directly before, because we've never had a hollow human-made object confirmed to strike a visible, observable part of the lunar surface, while cameras were actually ready and pointed in the right direction. And within days, that same debris field, whatever shape it ultimately takes, will very likely be photographed directly from lunar orbit, turning tomorrow's prediction into confirmed, measured, scientific fact. That's not a 100-year-old kind of story. It's a genuinely new kind of story, one that's really only become possible in the last few years, as tracking technology, orbital modeling, and easily coordinated global observation networks have finally caught up to the kind of precision this event actually required. The moon isn't doing something it hasn't done in a century tomorrow morning. It's doing something for what is, as far as anyone can currently confirm, only the second time in recorded history, and the very first time in a way that any of us watching from Earth will actually get a real chance to see happen.